So yeah, welcome back to the CS580 computer graphics. So last time what we have discussed is that we started to discuss like how we can apply the idea of like the Monte Carlo estimate in terms of like calculating not only the local illumination but also the global illumination. So we start to see some kind of the effect of the indirect illumination in terms of the if we basically accumulate the paths in the ray tracing with the multiple bounces. Like this was the case that we are only basically caring about some kind of the emission of the light from the light source. And then this is kind of the case that we are also accumulating the direct illumination with the single bounce of the paths. And if we start to basically accumulate some more kind of some indirect illumination, then we can start to see some kind of the more like natural kind of illuminations that is basically showing this kind of the outputs. So with some kind of the indirect illumination, we can also see some kind of the regions in the virtual 3D scene, which are not directly visible from the light source and also the viewing the camera direction, but some kind of like the parts that can be illuminated by some kind of the multiple bounces of the lights. So those are kind of some of the outputs. And for that, basically what we have done last time is that we are kind of like rewriting the reflection equation as kind of the light transport equation, which is basically having both the light source term on the left-hand side and the right-hand side. So in terms of that, we are having some kind of the recursive form of the equation. So we could basically rewrite the light transport equation into this kind of the 3-point form in terms of like having considering the area of the kind of regions and those the light sources. And when we basically introduce this new term, the G, which basically incorporates the visibility and also this kind of the cosine the terms, we can basically have this kind of the simplified the form of the light transport equation. So here, basically, the question is that how we're gonna basically calculate this kind of the complex form. So especially if we also rewrite this kind of the recursive form by substituting the light source parts with some kind of the calculation which is coming from the next kind of the bounce of the trajectory, we can see that actually the recursive form can be rewritten this like the way. So we are basically accumulating this kind of some light equation from the path of the length of the one, which is the case that we are just having like direct the emission of the light. And the path of the length 2 is the case that we are having the direct illumination. And path of the length 3 is the case that we're having the indirect illumination and so on and so on. So we are basically adding up all those kind of things. Then we can see that this equation can be seen as like this, basically adding all these kind of the terms denoted as the P, which is defined with the kind of a path, basically the ray tracing. Here, basically, this P bar indicates a kind of the trajectory of the ray tracing, which basically involves multiple kind of the bounces in the scene, and every kind of the point P is basically indicating the point of the surface that we are seeing some kind of the reflections of the kind of the lights. And then we can see that the kind of this P term can be defined as kind of the multidimensional integral over the path. While this basically looks complicated, this is basically kind of like nothing but basically we are multiplying the emission of the light from the light source with the throughput of the path. And this throughput of the path can be seen as kind of the fraction of the light from the light source at the Pn, at the end, like we are reaching to the light source, and then basically we are seeing the fraction of the light that is really coming into the point in the image plane. So when you basically calculate this kind of the multiplication of the light source and the throughput of the path, and when you basically add up all these kind of things for all the multiple passes that we're basically tracing in the scene, we can get the final basically the light information for every pixel of the image plane. So the simplistic idea that we can basically calculate these things using the multiplicity estimate might be is that basically for each of the p term, we are basically having the sample of the path. Then basically the multiplicity estimate for each of the p term can be defined in this way, having some kind of the multiplication of the light emission, the radiance, multiplied by the throughput, and also dividing this by the probability, or how likely we gonna sample that trajectory. And if we sum these up, then we can get some kind of the estimate with basically the final outgoing radiance that is actually coming into the pixel in the image plane. So that was the basic idea of some kind of the global illumination. And what we basically do with this kind of the ray tracing based the rendering system is basically implementing these things with some lots of some kind of details in the implementation. Obviously, we are not going to basically discuss all the details, but there are like lots of kind of some things that we can really consider, especially to make some kind of more efficient the Monte Carlo estimate. But we're going to basically see some kind of the very basic idea in the today's lecture. Before we move on to the, do you have any questions on this? So yeah, let's see. So basically here, all the thing is basically how we trace all the paths of the rendering, the ray tracing the system in terms of like calculating this kind of integral. And the first idea of like this was actually introduced almost like 40 years ago by like Kazuya in 1986. So this was kind of the first image which was basically rendered by this kind of ray tracing the system, which is called by just tracing the path of the lights. And this has been basically used in the many kind of the physically correct some kind of rendering the pipelines. And as you can see, as we have some kind of the more number of the passes, we can get some kind of the better the outputs, which looks like more realistic. So this is kind of the case that when you only have like one sample of the trajectory the per pixel, obviously there are many cases that we have some kind of the dark the pixels. And as we have basically have some more the samples of the trajectory for each the pixel, we can see some kind of the more slightly more the realistic images, but still there are some of the dark the pixels that are basically not really reaching to the light source. And as we have some kind of the more the number of samples for each of the single pixel, that we can get some kind of the more the accurate outputs. But as you can see, this is the case that we are having like 1024 samples for every single pixel. So when you want to think about the number of the pixels, you can see that this basically involves like huge computation to basically get this like single image. So to get the realistic image, like this is kind of like difficult computation that might be involved in to get some kind of this level of the realistic images. So it's basically all about basically how to make this kind of the rendering pipeline more efficient. So the main two questions in the ray casting, the path tracing the system is basically how do we basically estimate the value of the sum of the infinite number of these kind of the p terms with a finite amount of the computation. So with some kind of the best quality. And also given the particular the p term, how do we generate one or the more number of the passes to compute the Monte Carlo estimate of the multi-dimensional the integral. So those are basically some two main questions to make some kind of efficient the path tracing the system. So one simple kind of the idea that we're gonna also basically see here is basically this kind of example. So basically what we have seen in the previous slide is that obviously some kind of the shooter the passes. Basically, as you can see here, we can decompose the sum of all this kind of the p term with the multiple the trajectories into the kind of the sum of the kind of p terms for the shorter the passes. So p1 is basically the case that we're having the path of the length 1, which means that we are basically taking care of some kind of the light the emission. And the P2 is basically the basically for the path of the length 2, which is the case that we are thinking like the direct illumination. And this is kind of the case that we are starting to see some kind of indirect illumination with the path of the length 3. As we also have seen in the previous slide, actually, these kind of the three cases with some kind of shorter deep passes actually contribute the most of the part in deciding the final image. So while we basically have some kind of when we basically have some kind of the trajectory with the longer passes, can make some kind of the more realistic the outputs. Actually, the contribution of the longer passes is kind of the much smaller compared to the passes with the shorter basically the lengths. But basically, when you have some kind of longer the passes, that basically involves some like more the heavy computation. So here the simple the idea that we can basically do some kind of a calculation with some kind of the limited amount of the computing resource would be basically just like ignoring some this kind of the longer the passes. So for example, like we just limited the length of the path to be like and to be equal or less than the 3. Then we just like totally ignore this part, right? But this is not good in terms of that we are also making the bias in our the kind of the estimate. So obviously we totally just like ignore this kind of the terms with the longer the passes. Then we're gonna see some kind of the case that we are having some kind of the estimate, which expected value is not exactly the same with the integral that we want to calculate. So here basically the big one of the question is that how can you make the estimator to be unbiased while basically also reducing the competition, the heavy competition with the longer the passes. So that's basically what we typically want to do, right? Obviously we want to limit the length of the passes to basically limit the competition, the time and the power. But then here the question is that how we can still make some kind of the unbiased estimator in terms of like having some kind of the limited amount of the some kind of the length of the passes in the computation. And here the basic idea is basically the Russian roulette. So the question here is that we are basically defining some kind of the new estimator in this way. So let's say like the F4 is basically the estimator of the like sum of this like P term for the passes, which length is like 4 or longer than 4. So here the question is how we can make the computation like this part to be efficient, right? And in here, what we are going to do is that we are going to define some kind of the new estimator, which is defined like this. So here, basically what we are going to do is that we are going to draw a same kind of sample from the uniform distribution in the range from the 0 to 1. And we also have some kind of this threshold parameter, which is the Q. Also the Q should be basically in the range from 0 to 1. And if this sample has the value which is greater than this threshold that we set, then we basically have this quantity as the output. Otherwise, we are basically having some kind of the constant value as kind of the output of the estimator. So here, basically, what you can see is that so we are having the two parameters, like one is Q and the other one is the C. And if we make this C to be 0, then what we can say is that like these things are canceled out. Then basically, when the random sample is greater than this threshold, then we somehow scale the estimator, which is computed based on this, right? Otherwise, we just like give some kind of return like the value 0. So this is kind of like the new estimator. And can you quickly see like what to be kind of the expected value like this new estimator? So obviously here the basic idea is that the expected value of like this new estimator is the same with the expected value of the F4, which means that this is kind of like one way that we are making some kind of the unbiased the estimator, while basically having some kind of the chances that we can basically ignore the competition like this whole part. But we need to see like why we need to have this kind of some scaling and the offset term to make the unbiased estimator. So let's quickly check out whether these two are the same or not. Did everyone get this result? Yeah, so we can actually quickly see that actually the expected value of like this new estimator becomes the same with the expected value of the original estimator. So actually, basically here the idea is that we know that the passes with the longer kind of the length is basically typically giving some kind of the less contribution to the final the outputs. So we want to ignore with some kind of the some estimate with the longer the passes, but we just like simply just ignore this kind of the estimate, then that will basically result in some kind of the biased the estimate. So here the basic idea is that we are basically introducing some kind of the statistical delay to draw about those kind of things. So if you are familiar with the draw about kind of things in the neural net, you can see that this is kind of a similar kind of idea, right? So we are basically randomly draw out this kind of the longer pass the computation by just setting some kind of the threshold and also drawing some kind of a random sample from the uniform distribution. So basically, typically we set the C to be 0. And what we can do is that every time when you have some kind of the longer pass the computation, we basically set some kind of draw some kind of sample from the uniform distribution. And if this sample has the greater value than the threshold, then we basically calculate the estimate while scaling it with basically 1 over the 1 minus q. Otherwise, we just like stop the sampling and basically terminate the computation. So this is kind of the statistical the way that we can basically cut out some kind of the computation with the longer the passes. So that's also kind of the interesting kind of the idea. Then what you can see is that if we have some this kind of a new estimator that has the direct illumination and also like the light emission and direct illumination and also the length of the tree of the kind of indirect illumination and having this kind of the Russian roulette the estimator, then we can also result in this kind of the unbiased estimator, and we can also apply this kind of same the Russian roulette the idea for the every depth of the sample. So that's also kind of the some of the ideas that we can make some kind of more efficient the computation. But here also the question might be is that it's always good to have this kind of like Russian roulette. Obviously there might be some kind of the some things that we are basically compromising with this kind of the dropping out of the longer the passes. So some of the questions that we can think about might be is that like how much the variance will be increased, especially like when you set like this the threshold of the Q value, depending on how we choose this kind of Q value, how much the variance will be basically be changed. Obviously the variance will be increased, right? So there will be kind of less chances that we are basically converging to some kind of the right answer as we basically cut out some of the computation. So we can also think about like calculating this variance and see how much the variance will be increased depending on the threshold of the Q value. So this might be some of the things that we can think about in this collective Russian roulette system. And also the thing is that like these will be basically the cases that we are sampling the points over the surface of the objects. So the typical the kind of system of the ray tracing would be is that we are having some kind of the arrangement of the 3D objects in the scene. We are basically having some kind of surfaces of the some kind of multiple the 3D meshes in the scene. And then we will be need to basically sampling some of the points over the surfaces. And here the question is that every time when you basically increase the length of the path, how we sample kind of the new point in the scene. And also the typical idea for this is that we first sample a object based on their the surface area. So if we have some kind of the multiple objects in the, for example, like indoor scene with chairs and the tables, desks, like or some kind of the other walls, floors, many kind of things, we are first selecting the object where we are going to sample a point based on their kind of the surface area. And then for the sampled this kind of the object in the scene, then we are also sampling a point over the object with the surface. And then actually what we are going to do in this kind of like the path construction is that starting from the kind of the point in the image plane, we are basically constructing a path in the incremental way. So what we do is that for every point pi in the trajectory, we first basically sample the solid angle based on the BRDF that we have for that point. And then we basically generate a new direction. And then we simply basically, trace the rate and we find the next intersection the point, the pi plus 1. And we are basically repeating this process until we reach to the kind of the limit of this kind of length of the path, or until we basically reach to some kind of the light source. So this is like very simple, high level the idea. Obviously, there are lots of the details in the kind of the real system. And also one small thing is that we are not only basically sampling based on the BRDF, but because we are also computing, since we are also computing the LTE, the light tensibility equation as kind of integral over the surface, we are basically correcting this kind of sampling PD like this, based on the kind of the relationship, the differentiable, the solid angle, and the differentiable the area that we also have seen in the previous the lecture. So the relationship between these two was basically defined like this, right? So since we are basically now taking the integral over the surface, not integral over the solid angle, now we are basically not only sampling based on the BRDF, but somehow like rectifying the PDE, the PDF using this kind of the equation, but so in a way that we can basically sample based on the surface. So these are basically the basic idea about basically incrementally constructing some of the paths and also doing some kind of the path tracing to calculate the LTE. So this is like some kind of the high level the idea in terms of how we can really do the path tracing. But for some more the details, I recommend you to check out the code. So actually our deploying the assignment is not including the parts of the path tracing, which is actually might be complicated for the implementation. But while the path tracing is not included in the programming the assignment for your own the programming, actually the path tracing should be basically included in the base code. So I recommend you to check out in the code. And also more the complete version of the path tracing, I also recommend you to check out the physically based rendering the book. So they have like all the ideas about this path tracing implementation. Do you have any questions on this? So this was kind of the wrap up of some of the basic idea about the global illumination. And today, actually, the main topic is about the reflection model. So I'm going to briefly explain some of the ideas that we did not discuss in the previous lecture. So in the light tensibility equation and also for the reflection equation, we are basically assuming that the BRDF is basically given as kind of the material property for the surface. So BRDF was basically the bidirectional reflectance distribution function, which is basically defining some kind of the ratio between the differentiable, the outgoing the radiance, and also the differentiable, the incoming the radiance. So when you basically define this kind of ratio between these two, this is basically defining some kind of the properties of the material that we can basically separate of the surface of the objects. So we are going to discuss some of the more the details about the BRDF, and also so far we only discuss some of the cases that we are only having the reflection. But in the real cases, we can also see some of the cases that the light basically pass through the objects, right? So this is the case that we also see some kind of this transmission as well. So we're also briefly going to discuss some of the ideas about like how we can combine the reflection and the transmission as well in this kind of the rendering the pipeline. So before we get into the discussion about the reflection and transmission, let's briefly see some of the some major properties of the BRDF. So especially when you want to do some kind of like physically correct the rendering, we need to basically satisfy these kind of the constraints for the BRDF. The first property is that all the output of the all the output of the BRDF should be basically the non-negative number because we are not defining any kind of the negative quantity for any kind of the light, the radiometric kind of things. There's no basically negative the quantity for the radiance over things. So obviously the BRDF, this kind of ratio also should be some kind of the non-negative number. So this is the first property. And for many kind of the some physical the situation also the reciprocity also should be satisfied, which basically means that if we have some kind of the ratio with the incoming direction and the outgoing direction, the opposite side also should have the same the ratio. So when you basically flip, the incoming and the outgoing direction. So we are basically having the outgoing direction as the incoming direction, and also the other way around. We also should have some kind of the same the ratio of this kind of the reflectors. So this is also kind of the secondary property, and this is also the property that actually we have seen in the previous lecture, the energy the conservation. Obviously, the total the energy of the light that is basically reflected from a specific direction should be equal or the less than of the energy that we are basically receiving as kind of the incoming light. So what we can see is that when you take the integral of this kind of the BRDF for the outgoing direction, the sum of this kind of the basically sum of this kind of the BRDF for the all the directions of the outgoing light should be 1 or the less than 1. So this is kind of the property for the energy conservation. So what's the exactly case that we are having the less than 1 of this kind of the integral of the BRDF? If this kind of the integral of this kind of BRDF for the outgoing direction is less than 1, not equal to 1, then what would be kind of the such kind of cases? Question 2. So the question is like, what would be the case that the integral like this BRDF for the outgoing direction is less than 1, not equal to 1? Yeah, obviously there will be the case that the light is basically the power of the light was basically observed. Some portion of the power was basically observed by the surface by the reflection. So when we basically see that this is basically exactly equal to 1, that's the case that we are basically conserving the energy without any kind of absorption of the light, the power of the light. But if this integral is basically less than 1, that means that the sum of the part of the light, the power, was basically observed by into the surface with the reflection. So this was the case. So we also have seen that like we need to basically satisfy those kind of things, not to basically see some any kind of the divergence, some kind of the explosion of the light power in the previous diffuse the sphere case in the previous lecture. So these are basically the main properties for the BRDF, and also some of the other properties that we can think about might be is that whether the BRDF will be isotropic or the anisotropic. So for many of the cases, for some kind of the papers, for some kind of the paint, many kind of the cases, actually we are seeing some kind of the isotropic material. So the isotropic material is defined in this way. So if you choose a point on the surface and rotate the surface around its the normal axis at the point, then the distribution of the light reflected at the point does not change. So this is kind of the case that the definition of kind of the isotropic material. So this means that while we fix the direction of the incoming light and also kind of the viewing direction, if we only change, rotate the surface of the kind of objects with respect to the normal direction of the point that we are seeing some kind of reflection, then the distribution of the light reflected at the point is not being changed. So for those kind of the cases, typically for the BRDF, we are basically having some 4 parameters, right? We're having the speaker the coordinates for the incoming light direction and the outgoing the right direction, which means that the typical BRDF will be 4 parameter the function. But if we basically assume that we are having the isotropic the BRDF, then we don't need to actually have the 4 parameters. Actually, 3 parameters suffice. Then how can you also define some kind of the 3 parameter function for the isotropic the BRDF? With this definition of the speaker the coordinates, basically the theta is basically indicating the elevation, and the pi is indicating the azimuth, right? So this is actually the case that we are only rotating, we are not rotating kind of like incoming light direction or some viewing direction, but rotating, for example, the surface. So when, for example, like when the surface is like the paper, like think about that, like we are having some kind of the paper on the table and we are rotating the paper on the table while having the same the environment of the light and also the viewing direction. And we see the same distribution of the light, those cases. So basically, this means that like actually this is not the case that we can just ignore the outgoing the azimuth of the outgoing direction. But actually what this basically means that we just need to consider the relative the azimuths between the two the incoming and the outgoing directions. Does it make sense? So if we want to see some kind of effects that we are seeing some same distribution, whatever kind of the some rotations of the surface that we see, then we can actually define the BRDF in terms of having the elevation of the incoming and the outgoing direction, and taking actually just like relative the azimuths between the two directions. So this is kind of like the way that we can define some kind of the three-parameter function for the isotropic the material. So which is kind of like some more general cases we can see in many kind of the real the objects. But obviously there are some kind of the anisotropic the material, which is basically having some kind of the some patterns of the over the surface. So for the like CD here, or some kind of the hair and the clothes, for those kind of the cases, we cannot define some kind of three-parameter DBRDF, but those are some kind of the anisotropic the cases. We need the 4 parameters. So those are some kind of the basic properties that we can think about the BRDF. And if we just review some of the basic types of the reflection, which is defined with some kind of a BRDF, then we can also, as we also discussed in the previous lecture, we can think about some either the spectral the reflection, and also either the diffuse reflection, or some kind of the other types of the some spectral refractions. So if we briefly review those kind of the ideas, for all those cases, what we can think about is that if we only care about the the azimuths of the light. So when you basically define some kind of local coordinates with respect to the normal direction of the surface, if we only see some kind of the projected direction of the lights at the surface, which is basically defined with the kind of the surface normal here, then we can see that the projected the direction of the light always basically goes straight, right? So the light was basically coming like this in the projected direction, and the projected direction of the outgoing the light should be basically the same direction, right? Going to the same. So we can see that when you basically have the direction to the kind of the viewing kind of the viewer here, and also the outgoing the direction to some kind of the objects, we can see that the azimuth was basically flipped 180 degree in this kind of the projected space. While when you consider some kind of the elevation of the angle of the light, then for the either reflection case, then we can compute this kind of the elevation of the outgoing direction and also the incoming direction with the rho of the reflection, right? So this is also a thing that we could learn in the high school kind of things, right? So when you basically define some kind of the angle of the incidence of the light, angle of the incidence of the light here, and also the angle of the reflection, which are basically defined with respect to the surface normal, we can basically define some kind of incoming and the outgoing direction in a way that these two angles to be exactly the same for the elevation. So this is basically simple the rho of the reflection. And here also the thing is that in terms like computing the reflection equation and also the LTE, the path tracing, these basically result in this kind of the Dirac delta the function for the BRDF, right? So if we think about basically BRDF, this kind of like ideal the spectral reflection, we only have some kind of some constant value when the incoming direction is exactly the same with some kind of the reflection direction of the outgoing the direction, right? Otherwise, the function should basically return 0, right? So basically, this will be the case that we are basically involving some drug delta function in our BRDF. That means that when you take the integral of like this kind of like reflection the equation, actually the integral like this equation will become some kind of the value that we can directly compute. So in this case, we don't need to basically compute any kind of the Monte Carlo estimate. We can just directly see what we kind of the direction that we need to shoot the ray in the ray tracing, and we can just directly compute this kind of the light outgoing the radiance. So would it be good for the ray tracing the computation or not? Do you think that like, so if we only have some kind of the ideal speculative reflection of the materials in the scene, do you think that this will basically make this kind of like computation easier or not? Any thoughts on this? So we can think about some kind of some very like, of course, some sort of the indoor scene that is like composed by some kind of all the glass-like the objects in the scene, some crazy room. That we're gonna basically render the things using some this kind of the BRDF that involves the drug delta the function. That looks like we can just like avoid the computation of the Monte Carlo estimate because we don't need to take the integral, right? Then what of the issue that we are having this kind of the involving drug delta the function in the equation? Actually, like, having this kind of like directly function, like involves many kind of the challenges in the ray tracing, because like if we have some kind of the distribution, in our BRDF, then we can sample some of the points in terms of that, we can reach to some kind of the surface, some kind of the point. And at the end, we can really even like sample the points over the light source in terms of that we can really get some kind of the computation from the light emission from the light source, right? But if we only have the ideal spectral reflection, which means that there is like only one specific direction that we can really get some kind of the some contribution of like this kind of equation, right? Which means that there is no sampling of the direction. There is only one direction that we can basically shoot the ray in our path tracing. And we don't know how many kind of the balances that we need to reach out to some kind of the one of the point of the light source. Actually, in some kind of the worst cases, we may need some kind of the tones of kind of the reflections, the balances to reach out to some of the one of the point in the light source. Which actually means that while it looks like we are making the computation easier, actually it can involve some kind of the computation with the very long the path of the computation. Otherwise, there is no way that we can really calculate this kind of the integral. So if we actually have some like all the cases that we are only having the ideal the speculative reflection, the computation actually becomes much more challenging in terms of that actually we may need some kind of the very long the passes of the trajectory to reach out some of the points in the light source. So actually, this is not that easy case to get some kind of the some kind of the realistic to render the images. Obviously, in many kind of the real cases, it's hard to assume that we are having some perfect spectral reflection. We're gonna see this kind of some sort of the glossy reflection that we are having not exactly shooting the ray into the opposite direction, but having some kind of the distribution near this kind of the opposite direction, right? For those cases, so we can define the glossy reflection like this by having some kind of the some sort of the dot product between these two with some kind of the power of this kind of the dot product while controlling this kind of the distribution of the lights with the kind of the power term here with the parameter here. So this is like also the simple the idea which was introduced in the 1970s by Blin and Defoe. So this is called the Blin and Defoe reflection model for some kind of a glossy reflection. For the also diffuse the the reflection for the perfect diffuse reflection, because this is the case that now also the BRDF becomes some kind of the constant value. So when you define the BRDF as the constant value like this with the rho over the pi, then we can say that the reflection equation can be calculated like this. So it's basically just nothing but multiplying this constant value by the incoming the irradiance, right? So this was basically the definitions of the irradiance. So we can basically compute the kind of the reflection equation by just taking the multiplication like this constant with the incoming the irradiance. So yeah, actually this is like one of the reasons like why we are defining the BRDF as kind of the ratio between the incoming, between the outgoing the differential irradiance and the differential irradiance, because like then we can define the ideal the diffuse reflection is kind of the constant term like this. So here one of the question might be is that like why we are defining this constant term as not just like the one single value, but as basically the rho over the pi. So here the question might be is that what's the meaning of the rule here, right? Can you guess what's the meaning of the rule here? Why don't just like don't you define this as kind of some constant value C here? So actually we can see that the rho means the kind of the ratio between the outgoing the irradiance and the incoming irradiance. So for the diffuse the reflection, what we can say is that the outgoing the irradiance should be the constant over the all the directions, right? So if we also compute the outgoing the irradiance in this way, then we can say that actually it is defined as kind of the rho times the incoming the radiance. So from the definitions of like how we define the BRDF, we can say that the rho term there is basically defining the kind of ratio between the outgoing the radiance and the incoming the outgoing the irradiance and over the incoming the irradiance, which should be basically less than one to basically have some kind of the satisfy the energy the conservation the property. So this is basically the way that we can define the perfect spectral reflection and also the perfect diffuse reflection, right? So this kind of the simple the BRDF for some very specialty cases, so like perfect the spectral reflection and also perfect diffuse reflection, and also some of the kind of the glossy reflection actually has been discussed even before like people start to work on some kind of the ray tracing. So if we just briefly review what we also have discussed in the introduction to computer graphics course in the CS380, typically even in the many kind of the some old kind of the graphics the pipeline, especially using some kind of the rasterization, we can say that the illumination, the local illumination, is typically kind of like represented as kind of a combination of some kind of the ambient light and also some kind of the diffuse reflection and the spectral reflection. So when you basically like just like add up all those kind of things, this kind of like simple the way that we can define some kind of the some local illumination, and this also has been used for some decades, even in the simple the restoration based the pipeline in the OpenGL. So this is still being used in many kind of the OpenGL the pipelines. while if we start to see some kind of some more complex BRDF, we can actually start to define some kind of the more realistic, physically collect some kind of illuminating the models with some kind of the more special the BRDF. So this is kind of like the basic idea and the connection with some kind of some old idea in the 1975. Any questions on this? So today we are also going to briefly discuss like how we can also define not only the reflection, but also the transmittance as well. So now we are also going to discuss not only the BRDF, but also the BTDF, which is now defining bidirectional transmittance directionality function. So when you also combine the BRDF and the BTDF, this can be also called like BSDF, bidirectional scattering directionality function. And also, I did not prepare these slides for today, but also there are some kind of more complex model, like the subsurface scattering. So here, what we are basically already assuming is that the light is basically reflected at a point like this, while like light is transmitted inside into the medium. So this is transmittance. But there are some of the cases that we can say that the light is basically going through inside some kind of the medium and popping out from the different positions. So this is the case that we are saying like the subsurface scattering. So we can also think about like defining some kind of the bidirectional function for those kind of cases. One quick question is that if we define this kind of the subsurface scattering, then how many of the parameters do we need? So for the BRDF, for some generality cases, we are also considering some kind of anisotropic the BRDF. We have seen that we need the 4 parameters, right? But if we also define some kind of the subsurface scattering, then how many parameters do we need? Yeah, it obviously depends on like how we define the subsurface scattering, right? But at least like we will need the 6 parameters, like 2 for the incoming light, 2 for the outgoing direction, and also the 2 for basically the direction that we are moving over the surface. So if we have the polar coordinates for this kind of like offset over the surface, then we will need at least like 60 parameters. So we're gonna also briefly discuss the basic idea about the subsurface scattering next time. But let's move on to some kind of the ideas for the transmittance. So as we have seen some kind of the examples, like having some sort of the reflection, now we can also see some kind of cases that we are having some kind of transmittance of some kind of the light into the surface. So how we can define some kind of the compute the direction of the transmission. So basically what we can see is that like we can recall some of the kind of the ideas that also we have learned in the high school kind of things. So we can basically calculate the outgoing direction of the transmission with this Snell's law. By the way, all the things that we are going to discuss for today is not any kind of the precise like simulation of all the optics kind of things. So you can say that this is like very simple, some kind of the approximation of some kind of some physical the ideas for some kind of the make some kind of the computation to be like efficient, right? So this is basically some very review of some kind of the very basic, some kind of the physical properties, and we are going to focus more on basically how we're gonna model these things for the computation, right? So if we briefly review some of the properties of transmission, basically this will be the case that we are having some kind of like one medium here, which will be, for example, like the air, and we are having another the medium, which might be like the water, like the glass, whatever kind of things, right? Then the light is basically coming from the air and then getting into some kind of the medium that can be the water or something, right? Then the direction, so when you have some kind of incoming direction of the light, the outgoing direction is will be basically determined based on the index of the reflection, right? Of each of the medium. So when you have the two medium, each of the medium will have may have the different index of the reflection, which is basically indicating the speed reduction of the light, each of the medium. And what we need to care about is that we only need to care about the relative index of the reflection. So when you have like the sine the theta I, then we actually need to just like think about like t sine t. So depending on like what's the kind of the ratio of the index of the reflection of the like the two media, we're gonna see that how much the light is basically dependent. So yeah, with this kind of like reflection, right? So here one quick question is the like if we have some kind of the relative index of the reflection greater than the one, then what's the kind of the bending of the lights that we're gonna see? If this like relative index of the reflection is greater than one, then what's kind of the trend that we're gonna see? Yeah, let me move on a bit quickly. So obviously this is the case that, I mean, this is very typical the case, like the incoming, the media will be typically air, right? Or some kind of vacuum. Or then the out, I mean, some kind of the another the medium might be something else, or which might be water or something. And typically in the vacuum, like the case, like, the index of the reflection is just like the one. And the index of reflection of the other the medium will be typically greater than the one, right? So this is the typical the case. So when what does this mean is that like when you increase this value, then this value will be decreased, right? So which means that the light will be bending toward the surface normal, like it's going like this, right? As the number is basically being increased, right? So the answer is that the reflected light will bend towards the surface normal, right? And actually, the opposite case will be this. So the question might be is that like now we can calculate the reflection the angle like this. But if the sine of the reflection the angle is greater than the one, then what the kind of situation that we're gonna see? For those kind of the cases, so as the sine of the reflection the angle like get closer to the zero, then what we're gonna see is that the light is basically reflected near the surface like this. And if this value becomes like greater than the one, then what we're gonna see is that there is no reflection. We're gonna also just see that the light is like only just like reflected without any kind of the reflection. Right? So this is kind of the typical kind of the cases that you can see. So based on this, what we can observe is that you might have have seen this kind of the image, like which is called the optical the manhole. So under the water, what we can typically see is that like the light is coming into this kind of the cone like the shape. And the reason why we are basically seeing that the sunlight is like coming into some kind of the cone like the shape under the water is that inside the water, what we can see is that all the lights are basically reflected only in this kind of the cone like the region. For all the other regions, we are seeing the total sorry. Yeah, basically we are seeing some kind of the total the internal reflection in the outside of region. So we are seeing some kind of the dark region outside of the cone, while we are basically seeing that all the sunlights are coming into this kind of specific cone. So that's why we are seeing this kind of like optical demand. And also some of the properties of the BTDF for the bidirectional the transmitters, the directional the function is that the BTDFs are basically not the reciprocal anymore. So which means that when you flip the incoming and the outgoing direction, the ratio can be changed. So this is quite obvious when you think about the kind of the properties of the transmitters, right? The transmission. And also the thing is that the index of the reflection is not constant over the wavelengths, but it can be actually changed depending on the wavelengths that we are basically having for each of the light. So which means that depending on the color, we may basically have some kind of different kind of index of the reflection, and also different the patterns of the kind of like the reflections, different angle of the reflection, right? So what we can typically see is that like when you have some kind of the constant index of the reflection, we're gonna see this kind of the rendered image. But if we basically apply this kind of some kind of the variance, so the index of the reflection depending on the wavelengths, then we're gonna see that the color is being changed like this in the final rendered image. So these are basically all of how we determine basically the angle of the reflection and also the reflection, right? And here also the question would be is that, so when you have some kind of the light, which is like coming into some kind of the boundary of the two media, how we can also determine the proportion of the light, which will be deflected and also the reflecting, right? So this is more about basically how much of amount of light will be basically deflected and also the reflected. So there are also kind of the lots of the theory in the optics about how we determine this kind of the proportion of like those like deflection. But basically long story short, what we can see is that when you see the light as kind of the electromagnetic wave, we are having this kind of the electric field and also the magnetic field, which is like orthogonal to the electric field. So if we just briefly see the basic idea here, we can basically see the light as kind of the two polarized lights, right? So one is basically the S polarized light, which is basically the case that the electric field is basically the perpendicular to the plane of the instance for those cases. And the other type of the light is basically the case, the P polarized light. Those is the case that we are having the electric field, which is parallel to the plane of the instance. So you can think that these are like the two types of the polarized lights. And depending on like this kind of the polarization of the lights, actually we can check that the proportion or like being reflected is basically being changed. So this is kind of the proportion of the light that will be reflected when we have the S polarized lights, and this is kind of the reflection of the proportion of the reflection when you have the P polarized lights. But when you basically simplify all this kind of the explanation and just see that like we're having some kind of the unpolarized lights, we can simply basically compute the proportion of the reflection into this kind of form. So this is kind of the Fresnel equation, and using this like Fresnel equation, we can easily calculate. Basically, it's kind of like simply approximation in terms of like calculating the proportion of the reflection into this way. But here, basically, one thing that we need to notice is that basically this kind of like the proportion of the reflection is also determined based on the angle of the incidence of the light. So this is basically not constant depending on the property of this surface, but actually the proportion is determined not only by the material properties, but also basically by the angle of the incidence of the light. So actually what you can see is that we can see this kind of the graph when you basically see that the light is like coming into the glass from the vacuum, when the relative index of the reflection is 1.5, then we can see that depending on the angle of the instance, the Fresnel, the coefficients, the fraction of the reflection is being changed like this. So this is the case that when you just like divide the fraction of the reflection, that the reflection is kind of the half and half. But when you basically calculate the proportion, more like correctly using the Fresnel equation, then we can see this kind of the more realistic the image. Then here the question is that how we can also compute both the reflection and the transmission using our kind of the LTE formulation, right? So this will be the case that when we have this kind of the reflection the equation, now we are having kind of the two factors. Like one is basically having some kind of the ideal the specular the reflection, and also this is the case that we're having the ideal specular the transmission, which is basically divided by the kind of the proportion that we are computing with the Fresnel equation. That what we can see is that this will be the case that we are shooting the ray for this kind of like the perfect specular reflection and transmission. We're gonna shoot two rays, like one is for the reflection with this proportion, and this will be the case that we are shooting the transmission ray with this proportion. Then we can do the same kind of the ray tracing with the the tracing in terms like for every kind of the bounce of the ray so intersection with the point, we are basically shooting the two ray. Like one is for the reflection, and the other one is basically reflection, transmission into the surface, and basically doing all this kind of the path tracing, which will basically results in basically some exponential growth in terms of the number of the rays, right? So every the bounce of the rays, we're gonna have the two rays, right? Then we're gonna see that actually there are lots of kind of some of the ways that we can construct the passes. So we can one of the way that we can also simplify this kind of the Monte Carlo estimate for those kind of cases might be is that we also randomly sampling either of the reflection and the transmission the rays based on the probability of which is defined with the Fresnel the coefficients. So when you also draw some kind of the random sample from the uniform distribution, when this sample has the value which is smaller than the Fresnel the coefficients, then we should be reflection the ray. Otherwise, we are shooting some kind of transmission the ray. So this is also kind of the statistical way that we can make some kind of the more efficient computation for the Monte Carlo estimate while basically choosing which of the rays we're gonna shoot, right? Some basic idea. And also some kind of the more the common cases that we're gonna face in many kind of the rendering the situation is that we are also having some kind of the thin plate with some kind of the some index of the reflection. So for example, let's think about that we are having some kind of the very thin glass in the air, which means that we're gonna actually have some kind of the two boundaries of the different the media. So for those kind of cases, when you have kind of like incoming ray from the air, then we're gonna see that we're having the one reflection and the transmission rays, and then we're gonna do these kind of things again at this surface, having another reflection and the transmission. Then we're gonna see that we're gonna repeat those kind of the things, having the two rays. Then this will be the case that we're having the transmission, reflection, and the transmission, right? And so all the reflection can be considered as kind of the accumulation or like those the black rays accumulating basically the reflection after also like transmitting under this kind of the medium, right? And also the transmission can be considered as kind of the summation, like all those kind of cases. So if you see like the reflection the case, this will be the case that we are just having the single bounce the reflection, and then transmission, reflection, transmission, right? And the next ray might be that transmission and the three reflection inside the medium, and also the transmission. And the next one might be that like one transmission and the 5 times of the reflection and then transmission, right? So we can think that like the reflection can be considered as kind of like accumulation of like all those kind of cases. Then can you somehow like make some kind of the simple form or like seeing some kind of the convergence of this kind of the series, right? So if we have seen that in the previous lecture, a Newman the series is basically converging to this, right? When basically the alpha is basically the less than the one. So when you assume that those kind of things, can you see some kind of what's the kind of some point that we are basically converging for those kind of these series? Let's only see the convergence of the R prime. Yeah, so as you can see, this will be the case that we are having this kind of the R term and T times R times T. And after that, what we are seeing is that we are having like two more reflection, right? So we're having two more reflection in the transmission and two more reflection in the transmission. So every time we are basically multiplying R squared. So what you can see is that this is the same as basically R plus, and then we are basically starting with the T times the R, and then we're gonna see like 1/1 minus like R squared, right? So we can see that actually this is basically the same, that now we are slightly modifying the fraction of the reflection by adding this amount of the term, right? While from the energy the conservation, what we can say is that T prime also should be basically the same with the 1 minus R prime, right? So we can say that from these kind of trees of the convergence like those trees, when you have like not assuming having some kind of some objects, but actually having like the shells like the object having only the surface in the scene, we can also calculate update basically the fraction of the reflection and the reflection, the transmission by adding this amount of the term into the proportion of the reflection, and also taking the 1 minus the R prime for the transmission. And you can see that in the graph, as we basically vary the angle of the incidence, actually the difference between the single interface and the double interface is not making big difference. But obviously you can see that the thin plate is basically having slightly higher the ratio of the deflection in this case. So based on that, we can also try to render some kind of the thin plate, like the thin glass like this. So those are basically the basic idea that we can also incorporate so transmission in the ray tracing the system. So I'm going to stop here. So actually, there are some of the ideas for the microfacet, the model for the scattering, and also I briefly mentioned about the subsurface scattering. So next time I'm going to briefly review those ideas about the microfacet, the reflection, and also the subsurface, the scattering. And so far, we assume that the light itself has been moving in some kind of the vacuum space, basically empty space. But typically, I mean, some real the kind of environment is not basically empty. We're having the air in the scene, and also the light basically may pass through the inside some kind of the smoke or water or something. So having some kind of the participating media. So for those kind of the cases, when you have some kind of the participating media, how will the rendering the system will be changed? Those are also the main topic that we are going to discuss next time. So this is the idea about the volume rendering. And if we also start to discuss the volume rendering, this is also the basic idea about the neural rendering technique as well. So we are also going to move on the neural rendering with the NERF idea, and also we are also going to discuss some very recent ideas about the neural rendering as well. So that's the plan for the next couple of weeks. And if you have any questions on those things, please feel free to post on the questions on the Slack. So we can also discuss on the Slack after the lecture. Any questions? Okay, then I will see you next Monday. Yeah. Thank you. Bye.